let me begin by telling you something maybe which is not very pleasant for everybody. I have.
No, we're not starting yet.
I will. Okay, fine. I will wait. Still 2 minutes now from now, isn't it?
No, maybe just 1 minute.
Okay, tell me when I can go.
Oh, okay.
How many people are with us for the moment?
So it's 23 of us at the moment.
Excellent. I'm happy that many people have came.
All right. Hello and assalamu alaikum, everyone. Welcome to today's seminar in the John Conway Spirited Seminar Series of Math Departments at LUMS. Today we have a speaker, Professor Rached Mneimne from University du Paris, and he is for Institute of Mathematics du Jussieu. He has interests in a whole lot of things. He's a very, very prolific author of several books in France, very celebrated. He's worked on linear algebra, finite groups, analytic geometry, Lie groups, their homogeneous spaces, and representation theory of Lie algebras. So today he's going to talk on Galois correspondence for babies, the case of polynomial, which is x raised to power 6 minus 2. Over to you.
Thank you, Hania. And I must begin by telling you, by confessing a small thing. I have distorted a little bit the truth by saying that my talk will be about babies, for babies. So I will, it's not for babies, okay? So this is my first confession. The second, that it is the first time I use Zoom to make my talk, so I'm a little bit anxious about the way it will happen, so be forgiveful. I have 50 slides to show you, and this means that the talk will last till the iftar. And Hania told me already that everybody has taken his nap and her nap, so we will be together for at least 3 hours from now. No, this is also a lie. So let us go directly to the heart of the matter. Let me go ahead. So peace on each one of you and good health for everybody. Let us go ahead. I will take off my hat because it's hot in Paris. It's around 17 degrees, and in my office, it is already 25 maybe. So the heart of the matter is the Galois correspondence. What is it? In a very quick way, it's a two-way bijection. We'll call this bijection gamma, and its inverse gamma minus 1 between two lattices, which are equipped with additional structures. I will tell in a moment what is a lattice. And one of these lattices come from field theory. It will appear on the right, and the other one appears on the left. It will come from group theory. Why Galois correspondence is nice? Because it's a bridge between two apparently different subjects, and for students, it helps them to appreciate quite well the unity of mathematics. So let me go ahead. So the picture is the following. We have a lattice L. We have a lattice L prime. Okay. And what is happening that these lattices are equipped with gradings and with actions of a same group, which we will denote G. I will not speak about grading, but because at the moment it will appear quite well and it cannot escape your attention. You will see quite well what is a grading, and the action should be defined quite carefully, and the introduction of the group G also. So this will appear at the right moment. For now, what I want to tell you that we have gradings and actions, and the map which is between the two lattices is not only bijective, but is of course monotonous, because it respects all the structure which are present in our picture. I would like you also to be attentive to the following. Here I have a sign. This is another sign. This one is \2. This one is maps 2, and the third one will arrive in a little moment. It will be leads to. These different signs are different. Okay, that means when I use one, I mean it, and when I use the other one, I mean it also. So what I want to tell you that here, our lattice will be very often a lattice of subsets. So we must very well distinguish this map, this arrow from this one, because we will not understand what is happening if not. Okay, let me keep in mind this idea. The Galois correspondence is a bijective correspondence between two graded G lattices. This is the idea which one should keep in mind. So being a correspondence between two J lattices, it will be J equivariant. This is the way a good map acts when we have J actions. And in particular, such a map will send an orbit in one situation to another. So let us go ahead, and I give you the summary of my talk. It will be in 5 parts, essentially 4 parts, and the last one, if you have enough time. The first part would be about lattices and J lattices. The second one about the Galois extension of the hello, Imran, how are you? And the second part will be about Galois extension of the base field, which is Q. And the third part will be the statement. We will devote enough time to understand how things work in the special case of the extension Q 6 root of 2 with J when we are looking at the polynomial x to the power 6 minus 2. It's a good example and it illustrates quite well the Galois correspondence. So what is a lattice? A lattice is simply an ordered set. An ordered set with a condition, which is very important. When we have 2 elements, we have a least upper bound and a greatest lower bound. And what should be the norm between lattices is just a map respecting orders. That means it will be an increasing map or a decreasing map. But in all cases, what we will have here will be a decreasing map in our situation of Galois correspondence. So what are the first example of lattices? Of course, the first example of lattices is the set of all subsets of a given set with the inclusion order. And the other example is the set of all divisors of a given integer with the order given by the divisibility relation. And in these examples, the things are clear. The least upper bound will be the union in one case and the LCM in the other, while the greatest upper bound will be in one case the intersection of subsets and the GCD of the divisors. Okay, so let me give you a small picture. When we have here the number n equal to 12, we have all the divisors 1, 2, 4, 3, 6, and I put them in a small lattice. We will see what which is here, and the lattices which are with us, one side of the group will be the lattice of subgroups of a given group with the inclusion order. Here we will look at the group generated by the union, and the other side we will look at the intersection of the subgroups, and we will have a lattice. So let us see what is happening. On the right, look very well what is the lattice of the cyclic group Z over 12Z. We have the subgroup generated by 6, generated by 3, generated by 4, generated by 2, generated by 1, or any number which is prime with 12. And on the left, I have put again the lattice of the divisors of 12, and you will see that if I have a divisor, I will send it to the subgroup generated by the class of D, and we see 6 is here, but the group generated by 6 has just 2 elements. So here the order is inverted. This is a nice example, very basic, where we have on the left the set of divisors of n, and on the right the subgroups of the cyclic group Z over 12. This is a very, very, very primary example. So everybody should begin by working Z over NZ, which are not trivial, but I think you have already done. So let us look at the various examples of elementary subgroup lattices. Let us begin with this group. I will have denoted it by T2. It's a dihedral group of order 4. That means it is C2 times C2. The cyclic group C2 with 2 elements times C2. How we can see it if we are looking with our eyes? We will see it in the affine Euclidean plane. The only possibility is it appears with 2 axes which are perpendicular and their intersection. Okay, so we have the 3 elements of C2 times C2 which are involution. That means elements of order 2, a reflection with respect to a line, a reflection with respect to the perpendicular line, and you have the half term. And physically, we can see it each time we have in a figure in a picture a rhombus or a rectangle. We can be sure that we are with the sense of it is the presence of 2 involutions which commute, and the third element will be their product, which will be also an involution. So let us say, outside my subject, if we are looking for the classes, conjugacy classes of can have 2 perpendicular hyperplane, 2 perpendicular plane with their intersection. That means I take the reflection with respect to each one of these planes and the reflection with respect to their intersection. And the third possibility is when I have this picture, that means a perpendicular line to a given plane with the central symmetry here. That means the central symmetry is clear. So how we can see in the Euclidean plane the group C3? That means the cyclic group of order 3 will look at each time there is something which is invariant under a third term. We can see that we have a C3. And when do we have something like S3? S3, I'm looking for the symmetric group of order 6, which everybody knows how to denote it is S3. It is the dihedral group D3, that means the dihedral group of order 6. It will appear each time we can see a kind of equilateral triangle. And in that case, you see we have here 3 elements of order 2 which are given by the symmetries with respect to these axes, and the 2 elements of order 2 which are given by the third turn in one direction and the third turn in the other one. So looking after D3 is easy in the plane by looking at equilateral triangles. Now let us see what happened with the group D4, the dihedral group of order 8. There are some authors who call it D8. It's bad because it comes from the square. It should be denoted D4. And remember that S3 is not S6 because we never write S factorial n. You understand? You understand with me what I mean. So here, let's begin by enumerating the elements of the isometries which leaves invariant a square. We have the reflections with respect to these principal axes. I would call them principal axes. The reflections with respect to the diagonals. This is 4 involution. We have the half turn here. This is a 5th involution. We have the rotation of a quarter of a turn in one direction and in the other. This gives us 7 elements. And of course, we shall never forget what is the most important element in a group. It's the identity. So if we show the lattice of D4, look at it quite well. It appears here. Okay, let me show it again. It appears here. And let me say that here they are the principal axis. Here are this one and this one are the reflections with respect to the diagonals. This is the center of the square. This is the half term, which commute with everybody. These are the 2 elements of order 4, which generate a cyclic group of order 4. And the picture of the 4 is here. So when I look to this picture, I see the square. So each time you look at this picture of the lattice of the subgroups of D4, you are looking at the square. Okay, this is important. And what I must add that I have put here some dotted lines. This means that these elements are conjugate under the action of an inner endomorphism. Why? Conjugacy in the case of algebra means in geometry looking similar. Okay, the diagonals look similar, the principal axes look similar. So here we have conjugation, and we begin to understand what does mean an action of D4 over D4. We are making D4 acting on itself by conjugacy, by inner automorphism. Okay, we can let it act by automorphism, but it's not interesting for us. We will be just looking at inner automorphism. You see, these 2 groups are normal because they are of index 2. There is no dotted line between them, which is very normal because all the 3 here are of index 2, so they are normal. But in fact, these 2 groups are what we call conjugate by an outside automorphism and an outer automorphism, but it's not important for our problem. Our problem will be G, which is operating on itself by inner automorphism. I have pictured also in this page the other group of order 8. We have here the cyclic group C8. We have here the group C4 times C2. Here the classical group H8, what we call the Hamiltonian group of order 8, the Quaternionic group. And this group, if you look quite well, there is no dotted lines. Here, of course, it cannot be dotted because they are of index 2. And this one is the center and it's unique. It's not dotted to anybody else. So this is an example of a group where everybody is normal, but who is not commutative. There is still a last group which I haven't represented, which is C2 to the power 3. And this one, its lattice is a little bit complicated. If you have time at the end, I will show you a way coming from the Galois correspondence, which can make us discover its lattice very easy. Okay, let me pass now. This is this part is the first part. I have finished with it. Let us pass now to the part about field theory and the Galois extension. Usually when authors speak about Galois extension, they have 2 fields, a small k and a big K, which are one in the other. And they say that we have a Galois extension if the extension is separable and normal. No need to get busy with separable extension. Here we are working with characteristic 0 fields. So separability is already given. Now, for us, so here Galois extension is the same as normal extension. Okay, because we are in characteristic 0. So you see, here we are speaking about normal extension, and we have already spoken about normal subgroups. So this is not the fact of the hazard or the it's well desired. So in our context, Galois extension and normals are the same. And let me look at some examples. This group, this field is generated by the roots of x3 minus 2. You see this one? I take the roots of x3 minus 2 and I look at the group, the field generated over Q by these. This will give us a Galois extension of Q. This one is not Galois extension. Any extension of degree 2 of Q will be Galois. Now, what is a Galois extension? For the moment, I haven't yet said, but what I want to tell you, yes?
Professor Rached, just recall what is the normal extension?
Yeah, this is what I will go. A normal extension is the same as a Galois extension for us, and I will tell you what is a Galois extension or a normal extension over Q. This is very easy way to do it. Look at this sentence. A Galois extension or a normal extension of Q is just a field containing Q and which has just a unique replica inside of C. Let me explain this in other words, that if you have another field inside of C, which is isomorphic to Q of square root of 2, then it will be equal to it. I insist on this. You have here two fields, Q of square root of 2 and Q square root of 3. These two fields are of dimension 2 over Q. As vector spaces, they are isomorphic, but they are not isomorphic as fields. Okay, there is only one copy inside of C, which is isomorphic to Q as square root of 2. It's a unique inside of C. The same for Q square root of 3. This is a very easy way to understand Galois extension of Q. They are unique. You cannot have another copy of them inside of C. Okay, so this is not maybe satisfying for everybody, but for me, I find this way to understand the normal extension very good. Another way is very easy. You take any polynomial.
Excuse me. What do you mean by that they are not isomorphic as a field?
Yes, let me tell you why they are not isomorphic as a field. And this one, on the left, you can solve the equation x2 minus 0. Okay? x2 minus 2 equals 0 has two solutions in this field. Okay?
Yes.
And this one, you cannot solve x2 minus 2. Or if they were isomorphic, you can solve the equation in because an isomorphism between these two fields will take any element in Q to an element in the same. Automorphism of fields will leave any element of Q fixed. Why? Because they would send 1 to 1, 2 to 2, 3 to 3, 1 over 3 to 1 over 3.
Got it. Got it now. Got it now.
You get it now. Any automorphism here will leave any elements of Q fixed. So if we can solve on the left the equation x2 minus 2, we will solve it on the right, and this is not possible. So this Q of square is the unique field subfield of C where you can the minimal subfield of C where you can solve x2 minus 2 equals 0.
So what I understood, it means the isomorphism should be a member, one of the member from derived from the automorphism of Q square root 2.
I didn't hear.
So you mean that any isomorphism between Q square root 2 and Q square root 3 should be derived from the automorphism of Q square root 2?
No, there is no automorphism between Q square root 2, and there is no possibility to find an isomorphism between them. But here we can have automorphism of Q square root of 2. Let me show you. Yeah. You can take A plus B racine 2 to A minus B square 2 of 2. This is an automorphism.
Yeah. This is what I understand. This is what I understand.
Okay. On the left, we have automorphism. But
I was just thinking about. What about sending square root 2 to square root 3?
You cannot, because the square of 2 is equal of square 2 of 2 is equal to 2. The square is equal to 2. So if you send it on the right, you will have the same, or there is no square root of 2 inside. Square root of 2 doesn't belong here.
Yeah, okay. Got it. Thank you.
So this is a very easy way. You should keep in mind that a Galois extension is unique. No possibility to have a copy of it inside of C. Okay? Dr. Imran.
Yeah, thank you.
Okay, let us look at other examples. You see here, I will give you a way to have normal extensions of Q. Very easy way. You take a polynomial, anyone, irreducible or not, and you take all its roots, and you take the field over Q generated by these roots. For instance, if you take this polynomial, you see it is not at all irreducible. What are its roots? plus or minus square root of 2, plus or minus square root of 3, plus or minus square root of 5. The field is this one. Okay? Q square root of 2, square root of 3, square root of 5. Okay? And okay, everybody is following?
Yes,
No?
yes, yes.
And this field is a normal extension of Q. Normal. Okay? If we take this one, what is the splitting field of this polynomial, which is irreducible in this case? It's generated by 6th root of 2 and all its conjugate. That means all the multiple of this by any 6th root of unity. And between the 6th unit of unity, we have G, which is generator. So we can just take this one. This field is a normal extension of Q. Okay? And so it will be Galois. There is no other copy of it inside of C. Now, let us take another example. Am I able to have an example? Yes, very easy.
By J,
Yes.
you mean that by J, you mean the primitive root of 6 root
J,
of unity?
it's the usual minus half plus. It's the usual square.
6 root, yeah, 6 root of unity, usual.
J is a 6th unity, but it's not primitive. It is of order 3. You must take minus G or minus G2. Okay?
So it is not primitive, right?
J is not primitive of the 6 roots of unity, but it's primitive of the third roots of unity. But
Third root of
minus G
okay.
will do it. We are working with fields, so if there is G, there is minus G.
Yeah.
And if there is
got
minus
it, got
G,
it.
there is all the powers of it, and so we will have all the roots of this polynomial in this extension. And this extension will be normal over Q, will be Galoisian, will be Galois. Okay?
Got it. Thank you.
So very easy way, let me recall. We take a polynomial, we take all its roots, and we generate a field with them, and then we will have a normal extension. In books, in textbooks, you have a very complicated way to define normal extension. They will tell you if you have from this into C an automorphism, so it will come inside, it will remain in K. This is a very trivial way to understand also normal extension, because you see square 6 root of 2 cannot go to other element other than the other roots of x6 minus 2. So, of course, if you have an automorphism going from K to inside of C, it will take this element to its conjugate and will take G to its conjugate. So it take this group to itself. So it will come back. Okay? Normal extensions are inner. You see, I love to take this. Usually, when you get married, you ask for a conjoint which is outside the family. Here, if you are normal, you remain in the family. Okay, that means you have an automorphism. It will come back to K. You cannot go outside. Okay, this is normal extensions. So now let us look what is happening with the action of a group. We want a lattice and we want a group. What is the lattice? Very easy. There is a basic fact that the number of subfields of a given extension is always of finite degree. That means the dimension of K over Q is finite. In that case, the subfields are infinite numbers. This is not the case, of course, of subspaces. If you take this field, it is of dimension 3 over Q. You agree with me? Okay. This is the set of A plus B square root of plus C square of 4. These, it is of dimension 3. Okay. And as a vector space over 3, there are infinitely many subspaces. But there is no intermediate subfield. Why? Because if there is a subfield here, we will have a dimension here and the dimension here, and the product of the dimension will be 3. We are discovering the gradings. Okay, so here there is no field between Q of square and Q. No other field. You see, the only field possible is the extremes. Fine, Dr. Imran.
Yes, absolutely fine.
Okay, no possibility to have a subfield, while there are infinite possibility to have subspaces as vector subspaces.
Yeah.
So this is very important. in a finite extension, that means if the dimension is finite, then there are finite subfields. So this is our lattice. And you know quite well what is the subfield generated by two, the fields generated by two. It's K1 times K2, and the intersection will be the least upper bound, the lower bound, okay? The greatest lower bound, excuse me. So now, what is the group? Before answering this, let me tell you something. When you are working with a vector space, the geometric situation is controlled by the linear group, okay? If you are working with the affine space, the geometric situation is controlled by the affine group. If you are working with a group, you will look at its automorphism group to understand what things turn around. And if you don't want to work with the automorphism group, which is a little bit bigger, you will work with the inner automorphism. So each time we have a structure, we look at the isomorphism of this structure. So normally, we'll take here just when you have a field K containing Q, we will take just the automorphism of K. Remember that any automorphism of K will leave any elements of Q fixed, okay? But this group, very curiously, let us see it in the case of Q of square root of 2, there are two elements. You have the identity and the one which sends square root of 2 to its opposite. You see, I have used here the leads to notation. So the map is A plus B square root of 2 to A minus B square root of 2. So here we have two elements inside this group. Inside this one, no element except the identity. So this group, the automorphism of a field could be reduced to identity. And the less we have automorphism, the far we are from a Galois extension. In the situation of Galois extensions, we have a plenty of automorphism, the maximum possible. So why I say the maximum possible? Because usually this number, the cardinal, the order of this group is exactly a divisor of the dimension, of the degree of the field. And in that case, the number of the order, the cardinal, the order of the group automorphism of K divides the dimension of K over Q, and the quotient is exactly the number of copies of K inside of C. Okay, so if we apply this in the case of this, how many copies we have of this field inside of C? An easy exercise for students in second year university. We have 3 copies. We'll see it in a moment. If you haven't the answer quite immediately, we'll see it in a moment. So its dimension over Q is 3, and there is 3 copies of it inside of 3. So its automorphism group is of order 1. No other automorphism except 1. But before I come over, so we have the lattice L of Q, and we want something which operate over it. It's what we call the Galves group, which is exactly of K. It's the same thing, this group and this group. So I will use this one preferably. And this group operates on the subfields. How you have an automorphism, how we'll take a subfield to its image by an automorphism. So the action is quite clear. L of K, the subfields of K, the automorphism of K operate tautologically, almost tautologically on it. Okay, you have a subfield, you take its image under an automorphism. And it happens, this is very important, I have put it with the pink color, that any 2 subfields are conjugate if and only if they are isomorphic as fields. If you have isomorphism between the fields inside an extension, that means they are conjugate under an automorphism of the field, the extra field which is containing them. So when we will have the lattice and the action of the group on it, we'll put dots between isomorphic subfields. And on the left, remember, we have put dots between subgroups which are conjugate under the inner automorphism of our group. And this is the Galois correspondence. It will take an orbit on the left, an orbit on the right. But let us not go quickly and look at an example. I will go a little bit quicker here. And let me tell you, so we have Q, let me take something better. This is a field, and this is a field, and this is a field. If somebody asks you how to show that these three fields are isomorphic. And since they are isomorphic, we will put dots between them in the lattice. Why? Dr. Imran, you have an answer? Yes. It's because each one of them is isomorphic to the quotient of the polynomial ring
x2 minus 2.
by x3 minus 2. Agree with me?
Yes, yes.
And why? We can send x to one of these, either this one or this one, and I have not taken leads to, you see, and the three of them are isomorphic to this beautiful quotient, so they are isomorphic between each other. Okay, so now I want to give you the third part, which is the statement of the Galois correspondence. Okay, I come here, and this is the statement of the Galois correspondence. We read together, okay? So we are ready for it. We have on the left the lattice of J, the subgroup of J, on the right the lattice of subfields of K. What is J? J is just the automorphism, the group of automorphism of K. So let me erase this because we will not see anything after. So in each one, we have an action of G. So these are lattices with J action. And the gradings on the left will be the order, which are multiplicative. Subgroups will, a nested series of subgroups will have their orders, which will be in good situation. And the right, the degree of the vector spaces will play the same. So here, what is happening? What is the correspondence? We take on the left a subgroup of H. Remember, J is a group of automorphism. So H is a group of automorphism of the extension. And we take all the elements of K, which are fixed under all the automorphism of H. We will note this K of H. And on the other side, if we take a subfield, we'll take all the automorphism of K, which fix every element of small k, and we'll have a group, a subgroup. This one will be denoted like this, and this one will be denoted like this. So remember, without going inside, if you are seeing this for the first time, you will get perturbed about the definition, but the definitions are quite what we call natural. You cannot imagine any other correspondence between these two lattices other than the one which is given. And what we can say that the larger the group H on the right, on the left is big, the more you ask conditions on element to be fixed, the less its fixed point set will be small. Okay, the larger is the subgroup H, the smaller is the set of fixed point. So what we'll say about this, that the Galois correspondence will reverse the orders. Okay, like we have seen with the two lattices, the divisor of 12 and the subgroups of Z over 2. Now, here the group side on the left, on the right the field side. And what I want to tell you that this correspondence is J equivariant. That means if I take the subset of K, which is fixed under this subgroup, J, H, G minus 1, it is J. This is exactly the G equivalence. Okay, here again, it's very easy, it's natural, but if you discover this for the first time, it will appear a little bit difficult. So just keep in mind, the things fits well the condition. The gradings are respected, the actions are respected, and we have two lattices and they correspond to each other. What happens if the group on the left, the subgroup is normal inside of G? What will correspond to it as a subfield? In that case, the subfield will be Galois. And what is its Galois group? That means what are the automorphisms here? They form a subgroup of OT K, which is exactly the quotient of J over H. So things are quite nice. If you are looking at the lattice and you you take the quotient by a normal subgroup, you will have what we call a new group, and you can see it on the lattice. We'll take an example in a few moments. So let me go ahead. Is there any question?
Yeah, it should come other way around in the above example. G should come down and identity should upward.
I didn't understand, please.
Just go to your previous slide where you mentioned the example.
I will give you an example, many examples, but let me follow my slides and we'll arrive to examples. Okay. The examples will arrive in a moment. So we will now take our example. Our example is exactly this polynomial. Okay. And I will take the field generated by its roots. It's this one. Okay. Everybody agrees with it. This field is of dimension 12 over Q. It has just a unique copy inside of C. This extension is normal. Okay. And there are inside this extension exactly 16 subfields. How we will get it? Because we will prove that its Galois group is exactly the dihedral group D6, which has 12 elements and it has 16 subgroups inside. So we'll have 16 subfields. Okay, this is the Galois correspondence. Now we need to depict the lattice of the dihedral group D6. Okay, so look with me. On the left here, I have drawn the regular hexagon, and if we look inside the hexagon, we have the reflections with respect to its diagonals. These make us 3 elements. We have with these, which are the principal axes. So there is 6 reflections. There is the central symmetry here, the half turn, and we have the sixth turn, which will generate a cyclic group of order 6. Okay, this is the 6th turn. So these are the enumerating. We have enumerated the isometries of the regular hexagon. But inside of it, you see we have an equilateral triangle. Okay, this triangle, it is fit, it is done, it has its symmetry given by the diagonals. Okay, and if we take the other equilateral triangle which is inside, it has exactly the same group of isometries of reflections. So if we take this rectangle or we take this David star, it's the same. We will have exactly a D3 inside of D6. Okay. Other example, if we take now this rectangle, we have 3 rectangles. That means we have 3 C2 times C2 in D6. Okay. Everybody is okay with me? We look at the hexagon, regular hexagon, we see inside it 3 rectangles. So each rectangle is associated with a T2. That means C2 times C2. And there are 3 of them inside of D6. Fine. Now, let us go ahead and see what is happening. So here I have depicted the hexagon with its diagonals given in green. These are the principal axes dotted red. So here we put them on the left, the diagonals. On the right, I put the principal axes. They look the same, so they are conjugate. Remember that conjugacy, that means they look similar. This is very important. And what is happening here? We have here a rectangle. So this is a rectangle. This is another rectangle and a third rectangle. And if you look at a rectangle, very important, if you look at a rectangle, what are the elements? We have a principal symmetry and a diagonal reflection. Principal axe. And so D2 here will take one from this side, one from the other side, and the central symmetry. That means the half turn. So since the rectangles look the same, they will be conjugate, these 3. And this is normal because D2 is contained in D6. This is of order 12. This is of order 4. And this is the 2C law. And we know that the 2C laws are conjugate. So there is 2 ways to understand that these 2, either you see that they are associated to rectangles, so they look the same, so they are conjugate, or you see that they are the 2C laws of D6. So let us go ahead and see how many D3 we have inside. This one, we have seen it already. Its symmetries is given by the reflections with respect to the diagonal, but we have still another one. Inside the regular hexagon, we have 2 distinct symmetric group S3, which is the same as the dihedral D3, and you can see it here also. And we have again a David star, and we have this. And now the reflections are given by the principal axis. So now we look at what is happening with the group D. We have the group C6, which will contain a C3 and a C2. We have the D3 given by the blue diagonals, a D3 given by the red principal axis. Each one of these D3 will contain the reflections, the third term. And now we can depict the group D6. Here it is. Maybe I have a better picture of it. Let me show it to you quickly. It will be better. I'm sorry to, voila. Look at this nice picture, very nice one. You have here the group D6, the dihedral group of the regular hexagon. So I have the picture of a regular hexagon here. These pictures have been done by a very good friend of mine called Alain Debray. He's very imaginative with the TIC-Z, so he depicts very nice diagrams. And here we have the dihedral group D6. Here we have the two dihedral group D3. This one, the blue one, will contain the diagonals. We see them, you see. Here, this one will depict the principal axis, the three of them. On the left, they are conjugate. On the right, they are conjugate. On the left, they are conjugate. This is the group D2, and this is the picture. You see how beautiful it is? Nobody is appreciating the beauty of it. So here, when you look at this lattice, you will see the regular hexagon with all its symmetries. This is very nice to look at. Okay, here you have exactly the regular hexagon. This is the David stars in it, the combination of the two equilateral triangles given by the diagonals. This one with the principal axis. Here you have the rectangle which are inside. Okay, here you are the rectangle, and here you are the 7 elements of order 2. Now we have depicted the group D6. But why we are interested with D6? Because it's our Galois group. And why it is our Galois group? We know that the Galois group will be of order 12. Or if we look slowly, now it's the catastrophe as usual. If we work a lot of time with no possibility. Let me go slowly. I was afraid of a situation like this. Sorry, it will take maybe a little time, but if we don't do it slowly, we will have a problem. There are 5 groups of order 12 in mathematics. Here they are. We have 2 of them which are commutative. That means the cyclic group C2 and the product C6 times C2. These are commutative. The group alternate group A4 and the group S3 tilde, which has no name. I call it personally sextinions. And these are the lattices of each one of them. We have 5 possible groups. We should take away the 4 here and we'll remain with D6. Okay? How we'll take out all the 4 which are here? Very easy. First of all, we cannot have these 2 because they are commutative. So everybody is normal. Okay? That means all the sub-extensions will be unique. Or we know that inside we have Q and its conjugates, okay, and the third one. So since there are dots in the part of the lattice of fields, these ones are eliminated, okay. Now, why we don't keep this one? Very easy. A4 is famous because it has no subgroups of index 2. Okay, no subgroups of order 6 inside of it. Or subgroups of order 6 by the Galois correspondence correspond to fields of dimension 2. But we have fields of dimension 2. We have Q of square 2 of 2, which is in our field. So we cannot have this one because it has no subgroups of order 6. Now, why we can eliminate this one also? We can eliminate this one also because this one has a unique subgroup of order 6. But we, in our extension, we have Q of J and we have Q of square of 2. So we have 2. So this one is eliminated. Remember, the groups, the big groups, subgroups correspond to little sub-extensions. So here we eliminate this one, this one, this one, we will remain this one. So now that you have seen this, I will answer a question which was given by Dr. Imran. He told us, let us look at these groups, how you find the normal subgroups. The normal subgroups are represented with squares. Okay? Here there is just a unique non-trivial normal subgroups. And when you have subgroups in the lattice, you can see the complements of the subgroups, and you can see the inner semi-direct product. This is the nice fact about lattices of subgroups. They are wonderful. So if you are looking at A4 and you look at the subgroup, which we call the Kleinian subgroups, which is isomorphic to C2 times C2, generated by the double transpositions inside of A4, it has 4 complements, and they are all conjugates. So C4 appears at the semi-direct product of the Kleinian subgroup with C3. These are C3 subgroups. If I look at this one is normal, and it has 3 complements. This one is normal, but it has no complements, no possible. We should look at the complement. What is a complement? It's a subgroup which has the order of its index, and at the same time, its intersection with it is trivial. So this one intersects trivially with these, and they generate S4. So they are nice in position. Now, what is happening with this one? We have many possibilities. If I look to this D3, it contains the 3 elements of order 2. So these 4 subgroups here, 1, 2, 3, 4, are possible complements, and one of them is normal, which is wonderful. When we have a normal subgroup which has a complement which is normal, the group is the product, the direct product of this one with this one. It is the semi-direct of this one, but it's the direct product of this one and this one. Another thing, very important, let me see it here. If I look to this picture, okay, this subgroup is normal. Okay, it's unique and with its number, its order. Okay, it's unique with its order, it's normal. What is the quotient of S3 tilde by this one? So this is what we call the quotient lattice. It's very easy. What are the subgroups of G3 tilde by H, where H is this one? The subgroups of this one are in bijective correspondence with the subgroups of this group, this one, which contains H. So we can just look at this. Or what we see here, we see exactly the lattice of S3. So the quotient of S3 tilde by H is exactly S3. We can see it on the lattice. What is the quotient of D6 by this one? So it's not very easy to see the quotient of D6 by D6, but we know that the group is the product of these two. So the quotient of D6 by the center here will be also D3. So these are manipulation which should be learned to students very early in second-year university, and they bring happiness, and they are easy to manipulate. Once you have played with the lattices of groups, will be very happy. So just an example here, we can write D6 as the semi-direct of C6 with C2, C6, and we have just one element of order 2 in it, so it has 6 complements. So we can write it like this. We can look at C3. It has 3 complements. So we can write D6 like this. We have this D3, which is in red, this one, it has 4 complements. So we can write D6 as the semi-direct product of this by this, but it is also the direct product of S3 by C2. This will be helpful in a moment. Now we have depicted depicted what is the automorphism of K. It is exactly isomorphic to D6. I let you remember K is Q of 6 square of 2 with J. Now we will pass to the Galois correspondence. What the Galois correspondence, which we have already used by establishing this fact that the Galves group is D6, we must turn the lattice. Remember that the Galois correspondence reverse the order, the orders in our lattices. So we must turn and we'll get this. So this is the lattice of subfields. How I have obtained it by turning, with respect to an horizontal reflection, the lattice of D6. So here we have the field, here we have Q, and here the 3 subfields here are the here we have 3 subgroups of order 6. So we will have here 3 subfields of order 2. This one you have already known it. This one also. So what is the third one? It is not Q of G squared of 2. This is a usual error. It's Q of I square root of 6, because this one is Q of I 3. So when you take the product of these two, this one, you get this one. And this one is of dimension 4. And this is a Galois extension. Why? Because it corresponds to the C3. It is of order of dimension 4 over Q, 2 and 2. We see the gradings, 2, 2. And it corresponds to the C3, which is normal. C3 is normal in D6. So what is these? These are they are of order 3. They are conjugate. We have already said this. These fields are conjugate because they are isomorphic, and they correspond to the D2, which are on number 3 in numbers. So all this is easy. What is happening? All this is easy. This one is easy also because this group, this subfield corresponds to the central symmetry. It is here we get a normal extension, and which corresponds to the group C2 generated by the central symmetry. And see that we have 7 subfields of order of dimension 6. So these on the left are easy. This is 6 root of 2, G 6 root of C, 6 root of C, and G2 6 root of 2. They are isomorphic. They are isomorphic to this. So no problem here. The 6 are quite well. What is difficult is to get the names of these subfields. So this is my next. Well, here it's easy. I have in this situation the same. Here are my 3, and each one will contain Q. This one will contain Q to the power Q of the square root of 2. You take this to the power 3, you get this one. You take this to the power 2, you will get third root of 2, and so you have this one will take this one and this one. This one will take this and this one. So this picture is easy. This picture we have seen already that it is easy. Okay, this picture is easy. And now we are concentrating to see what is A prime, B prime, C prime. These are fields of dimension 6. They contain this, the 3 of them. They are associated here. So we must just give names for them. And to give name for them, we need the Galois correspondence. So let me go away ahead. So let us jump over this and look what are AB, A prime, B prime, C prime. If you remember, we have three rectangles, and these three rectangles appears in the Galois correspondence with these. So this is a rectangle, this is a rectangle, this is a rectangle. It corresponds to rectangle, and the rectangle is given by a reflections of order 2 and another reflections of order 2. So if we want to understand what is happening here, we should look at this rectangle, take the reflection which gives this, and take the perpendicular line to it, and we will have the fixed point of it will be A prime. So let us apply this in this situation. What is the reflection which keep, you see, here I have depicted the 6 roots of 6 minus 2, and we'll have this element, this is J, this is J3, and this is minus G2, this is minus G, this is minus, okay? So these are the roots of this polynomial. And what I see that this rectangle, which I have called it A, it fixes this one, and its perpendicular line is the principal axis. Okay, I have told you that when I work with a rectangle, there is a diagonal and the principal axis. So if I want an element which is fixed by this, it is easy. I take this element and this element and I add them, and I have an element which is fixed by this reflection. So the element is this one plus this one. And when I add them, I add G minus G2. That means I take this element and this, and this is exactly 2 times the imaginary part of J. This gives me 2. Let me write it. 2I times this. So I get this element, and this happens here. I'm a little bit in a hurry. Maybe I haven't been able quite well to show the picture. So now we are able to depict the other groups by the same way, B prime and C prime. B prime is obtained by this rectangle. It is given by this principal axis and this diagonal axis. So I will add this element and this element. I will have 6 root of 2 times A minus G. I have added this one and this one, I get this one. And when I will take this, I will obtain this. So these are the groups. And now we can have,
we have 5 minutes left so that we have some questions also.
Still now we will tell me, you will tell me, oh, why we have used the classifications of groups of order 12 to obtain our Galois correspondence. There is an easier way. Even if we don't know what is the classifications of the groups of order 12, there is a very easy way. We have inside our picture here, let me go back to the situation. We have here an extension which is Galois. And we have here an extension which is Galois. Okay, take this outside of it, okay? So if we look again, so let me take it like this. This is a Galois extension and its Galois group is S3. This is an extension which is Galois group is C2. And these two extensions, this one and this one, are independent. That means their intersection is Q and they generate the big one. So the Galois group of this one is the product of the Galois group of this one and the Galois group of this one. So it is S3 times C2. But if we know that S3 times C2 is D6, we are done with it. So this is a much better argument, which is quicker and will give us the answer. Still 1 minute if Mrs. Hania is okay with this. Now you will tell me we have in the plane just cyclic groups and dihedral groups. What about Galois groups, which are more complicated? So if we want a group which is C4 times C2, we must go in the space of 3 dimensions. If we want a geometric picture of a Galves group which is H8, we must go in 4 dimensions. We cannot have a picture of it inside of H3. So my argument passing by geometry is nice for dihedral groups, for cyclic groups and other subgroups which are finite inside the geometry of the space. We can play. You need to work with polynomials of order 8. We cannot have something less than 8. The argument is not difficult because you cannot have inside any group of order S7, S6 subgroups which are isomorphic to H8 in this direction. You need to go to groups to S8. S8 have a copy of H8. Why we are looking at S8? Because the Galves group operates freely and faithfully faithfully and transitively on the roots. So the Galves group will inject in Sn, where n is the degree of the polynomial. So this is the argument, and I have finished. One last thing: if you want to have the picture of C2 times C2 times C2, we look at this field and we write all its subfields, which are easy. Q of square, Q of square, Q of square. The product of this one, we have this one. The product of this one, we have this one. The product of this one, we have this one. The product of the 3 will have Q. We write the fields generated by 2 of them. It will contain the 3rd one. And we have the 7th subgroup. So this is the lattice of the subfields of this one. But by the Galois correspondence, it's the same as C2. So we have, this is the lattice of C2 times C2 without the names of the fields around. Fine? That's all. Okay. Any question?
That's wonderful. That's wonderful.
It is a catastrophe. It is a catastrophe.
Wonderful talk. I would like to invite any questions.
Please don't hesitate. Don't hesitate to ask.
Okay, I have a question. Okay, so in the lattice of the field, you have 16 elements.
In the lattice of subfields, I have 16 subfields. Yes.
Yeah. Yeah. So, and what about the Galois group of that? And you didn't show this.
Let me go to the lattice of my.
So what was exactly the Galois group for this field?
The Galois group of this extension is D6.
Mm-hmm.
The dihedral group D6. So there are 12 automorphisms inside of it.
Okay, so then it will have a similar lattice, of course.
This lattice is exactly the same as the lattice of the dihedral group D6, but which has been turned. Remember, the Galois correspondence reverses the orders. So you begin by depicting the lattice of D6, and I have told you how to do it. To construct the lattice of D6, you do essentially geometry. That means you look at the regular hexagon, and inside you see all the ingredients of the symmetry of it, and you picture them in the lattice. Okay, so.
Okay, if we go to the next, if you go to the next baby case is like the x power 7 minus 2 is equal to 0. I think in that case it will be much easier. Maybe x power 7 minus 2.
X7 minus 2.
That will be. I think
this will be D7.
Yeah, I think. Yeah.
This will be D7,
Really?
but D7 is easy.
So in general, I think this will not be D7. I think maybe it's cyclic. It will be cyclic or not?
It's it will be D7 if I'm not mistaken, and D7 is not difficult. You see, D7, the lattice, the lattice would be like this: 1, 2, 3, 4, 5, 6, 7. You have here something is C7, and you'll have D7 here, and it will be like this if I'm not mistaken. So
Okay.
it's not complicated, and it's not a very interesting example. The example with D6 has the advantage of giving something non-trivial. You see, the construction.
So I just I understand. So one last question. It's about Galois. Galois calculated for the 5th degree polynomial, or he did a lot of other cases also?
Let me tell you that Galois didn't touch anything about Galois correspondence. Galois was involved essentially by the solvability of equations of degree 5. Is it possible or not by radicals? And he proves with the help of Abel and Lagrange that we cannot solve the general equations of degree 5 by radicals. But there is nothing related to the Galois correspondence. The Galois correspondence has appeared later with the work of Emil Artin and other mathematicians who were interested by joining the aspect groups with the aspects of fields. Now we tell this Galois correspondence, but I think Galois has never to do with it. But in the same time, it's more elementary than the solvability by radicals. You see, what we have is to establish the correspondence between two lattices. But what I have insisted here in my talk, and in some sense it's a little bit new because you don't find it inside textbooks, that these lattices are equipped with G actions. And when you have G actions, on the left you will have conjugate subgroups, and on the right you have isomorphic subfields. And this is very nice, because by this way you can solve a lot of problems. You have seen how we have established that the Galway's group was D6. We have eliminated the abelian subgroups. Because all their subgroups are normal. And in the case of the fields, we have isomorphic subfields. So they cannot, the Galway's group cannot be commutative. Okay, this is the Galway's correspondence, taking into account the fact that we have J action. Another something which is a little new is the way to depict or to understand what is a Galois extension. A Galois extension is what is important about that it has no copy inside of C of it. So this is not Galois because there is copy of it. This is Galois because it's unique. And the fact that any extension of dimension 2 over Q, this is always Galois, is related to the fact that the subgroup of this of G is necessary, are deeply related by the Galois correspondence. Okay?
Okay. Thank you.
So these are the two facts which are a little bit new, which maybe they are not new at all, but they are not often seen inside the textbooks. The fact that a Galois extension is unique, no replica of it inside of C. And if you want to have the formula which is important, if you have K over Q, the number of automorphism here of K is exactly the quotient of the degree of K over Q by the automorphism of K. So if you make the quotient, you get the copies. If you want to see how many automorphisms is there of Q of square root of T, you see that you have 3 copies of it in C. The dimension is 3, so there is no non-trivial automorphism of this extension. Okay, fine. Please ask more questions, because these things are quite interesting and easy to answer. It's not very mysterious. sorry for my English. You see, living in France, we have not very often the occasion to speak English. And if I was among you, I would waving my arms and my hands, and maybe I would have been able better to explain what I was explaining.
Any other questions?
Do you want me to ask a question? Maybe I can ask you. If we take this extension, this polynomial, this is quite easy. It is in almost most books. Okay, what is it? This is D4. D4. It's easy to depict. It's like this. This is the Galois, the picture of the lattice. Okay. If the picture of the lattice is like this, of the field will be like this. Q of I field, and this most books about theory is more, but if work with H8, H8 has this as a lattice. The inverse of this will be like this. Sorry. So we will have a field K containing Q, which has three non-iso is A4. So this picture of Quaternionic groups. What happens here if you don't have any? You will have
what is the relation of these Galway extension with compass and ruler extensions?
with
So what is
a necessary condition, but this is not enough. You need to be able to jump by steps of degree 2 by 2. So if you are with an extension which degree is which Galves group is A4, imagine that K it's Galves group is A4. Okay, the alternate group, you will jump here from Q to a subfield which is of dimension 4. So the dimension is a power of 2, but you don't step by 2 by 2. So it is not constructible. Okay, so this is very important to keep in mind. To have a constructible element, you must arrive to it by jumps of degree 2 by 2. It is not enough to ask that it is of degree a power of 2.
Just out of a context question, what is the degree of extension of the field of all constructible element over Q? Is it countable?
Yes, the elements which are over Q constructible are countable. It's a field which is countable.
Which is countable. Yeah.
Yes.
Okay.
But I think what is nice is to get an example of an extension of Q, which has, as Galway's group, the alternate group A4. In that case, you will have elements which are of degree 4 and which are not constructible. This is the first example of elements which will be of degree a power of 2 and which are not constructible. And the reason why, because inside of A4, there is no subgroups of order 6. This is very common, well known.
Okay, okay. Professor Rashid, this is a wonderful talk, very exciting as usual. And
I'm sorry, Dr. Shahina told me that I will be registered, so please erase it as quick as possible and throw it to the garbage.
No, no, you are recorded here. Anyone who needs a recording of this talk, they can write to us. We can provide you the recording of this lecture. Hania, would you conclude this seminar? Hania, over to you.
Just a last word. Next week, I will speak about the fundamental groups of classical Lie groups. So come again, even if this one was a catastrophe, the other one will be for babies also. I'm lying again, but in trading world, distorted truth is good. It's not a sin.
Right. Thank you very much for a really nice talk. And we hope to see, thank you for joining everyone. And we hope to see you again next week. And you too.
Bye-bye. Bye-bye, everybody. Thank you. Bye.